Hello viewers, welcome to today's lecture on microprocessors and microcontrollers. We shall continue our discussion on instruction set, the vocabulary of the machine. In the last lecture, we have discussed two important aspects, the data types and the instruction formats. For example, so far as 8085 is concerned, we have seen that it supports only two types of data. One is 8-bit 2's complement integer number. Since it is 8-bit, starting from D0 to D7, this is how it is stored inside the processor. And the range is -128 to +127. It comes from 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. This is minus 2 to the power n minus 1 to plus 2 to the power n minus 1. So it has a very limited range and also very limited precision, 1 in 2 to the power 8, that means 1 by 256. If you want higher range or better precision, you have to go for larger number of bits, that is 16-bit or 32-bit. The 8085 also supports BCD data type in a very limited way. You can store BCD data in fact form. For example, you can store one number in the LSB 4-bit and another BCD number in the lower order 4-bit. Then two BCD numbers stored in this fact form can be added, obviously by using that binary adder, and the result can be again converted to BCD form by using a special instruction known as DAA, decimal adjust accumulator. So this decimal adjust accumulator is used to convert the binary data to BCD form stored in this fact form. Later on we shall discuss in more details about this special instruction DAA, decimal adjust accumulator. So these are the two data types of data supported by 8085. So far as instruction formats are concerned, 8085 supports three sizes of instruction: single byte, 2 byte, as you have seen, then it can be of 3 byte. So this is the three different sizes of instruction the 8085 supports. Later on we shall discuss in detail how this single byte, 2 byte or 3 byte formats are used to implement different instructions. Today we shall focus on the addressing modes of microprocessor. First I shall give an overview of the different types of addressing modes available in all kinds of microprocessor. Then later on I shall explicitly discuss the addressing modes provided in 8085. Now what is the purpose of addressing modes? The purpose of addressing modes is to provide some mechanism by which instruction, data and addresses can be referred in an instruction inside the memory, inside the register or from I/O. So with the help of addressing modes, you will be able to access instruction, data and operands. And there are several goals for realizing or implementing addressing modes. First one is to access large address space. Obviously, larger the memory, it is more convenient to write program. That means you have to access large address space. Obviously, this will require larger number of bits on the address bus, or you will require larger number of bits to be stored as part of the instruction so that you can access a very large memory space. For example, using 16-bit, which is commonly used in 8-bit microprocessors, the address space available is 64 k byte, where 1 kilobyte is equal to 1024, not 1000. You should remember that. And if you want larger address space, you have to use more number of bits. Second goal is specify addresses with smaller number of bits. You see, we want to specify the address with a smaller number of bits as part of the instruction. These two appears to be contradictory apparently, but you will see that in practice what is being done, normally your program is executed over a small part of the memory. As a consequence, using smaller number of bits, you will access within a very small address space, but you have the scope for addressing a large address space. Later on we shall come to this point. Then another important goal is easy implementation of popular data structures. You will see whenever you write some program or implement an algorithm, you have to use different types of data structures, and particularly in high-level language, different types of data structures are necessary so that data can be stored and processed efficiently for a particular algorithm. For example, array, linked list, stack, these are the common data structures which are used in storing data and implementing algorithms. Now, your microprocessor should provide some built-in mechanism so that you can easily realize array, implement array, you can easily implement stack, and so on. We shall see how the built-in features in microprocessors as part of the addressing modes are provided to realize array and stack in an efficient manner. Then the addressing mode should be fast and simple. That means to compute the address, it should not require additional hardware or take exorbitant time. So addressing mode computation to generate the address of a memory location or a IO location should be done in a very simple way, or should not involve complex computation. Finally, the addressing modes should provide easy implementation of modern software features. What are the modern software features? For example, one is position independent, position independency. Position independency is one important feature. By that I mean a program written in machine language, you store anywhere in the memory, it should execute. That is called position independent program. That means suppose a program is ROM based. That ROM you can put in any part of the memory and it should be able to execute. So irrespective of the location where it is stored. And later on we shall see how addressing modes will allow you to implement programs having position independency. Another important feature is reentrancy. Reentrancy means suppose you have written a subroutine and you want to, when the subroutine is under execution, you want to call it once again in between. Another program will call it once again. You are re-entering that subroutine. So to support that, you require some additional addressing modes. So we shall see how addressing modes are provided to support these features, to implement these features. So these are the goals, and we shall discuss various addressing modes provided in microprocessor in general. Then later on we shall come to the addressing modes provided in 8085. Here we are discussing the common addressing modes. First one is inherent addressing modes. And inherent addressing mode, essentially it belongs to that zero address class. although we are calling it as an addressing mode, it is essentially not an addressing mode. Actually, no addressing mode is used to refer any operand as part of the instruction. Here, the addressing mode is essentially implicit. Only the opcode is provided and the address is implicitly used by the instruction. For example, if it is a monadic instruction involving only one operand like not or complement, then you don't really require any address to be specified as part of the instruction. As you know, the one of the operand always comes from the accumulator and result is also stored in the accumulator. So in this particular case, the operand will be taken from the accumulator and the result will be stored in the accumulator. So for this instruction, just the opcode is provided. And for example, another example is halt. It does not require any operand to be fetched. So just the opcode is sufficient. So these are the example of inherent addressing modes. Then second type of addressing mode that is used is known as immediate. In immediate addressing mode, you are providing the operand itself. Say here is your opcode. Then the operand itself is provided as part of the instruction. Here is your operand. You don't require any address to be referred here, used here to point to the operand. The operand itself is provided as part of the instruction. If the operand is of 1 byte, it immediately follows the opcode. Otherwise, you may require another byte to store the second part of the operand. That means lower order byte and higher order byte. That means if your data or operand is of 8 bit, then you require only 1 byte. If the operand is of 16 bit, you require 2 bytes. This immediate mode of addressing is commonly used to store constant in your to store constant in your instruction. For example, you want to pass on the value of pi to your program. Pi has a constant value. That constant can be inputted by using this immediate mode of addressing. So you can have constant data values to be inputted, or sometimes it may be necessary to initialize some registers with some value. For example, you want to loop for 100 times. You have to initialize a register with the value 100. Then also this immediate mode of addressing can be used. So it can be used for initialization of some register. So immediate addressing is more or less provided in all microprocessors. Then the third type is known as direct or absolute addressing mode. In this direct or absolute addressing mode, what is done, the address is provided as part of the instruction itself. That means here is your opcode. Then you are providing the address of the operand as part of the instruction. Now, depending on what type of address you are referring, it can be of 1 byte or 2 byte. For example, in case of your 8085 microprocessor, the IO address is 8 bit, so that in that case you will require only 1 byte here. Or if you are referring a memory location where your operand is stored, then the address will be of 2 bytes. then this address will point to a memory location. This is your main memory, and here is your operand. So that address of the operand is provided as part of the instruction, and this is possibly the most natural way. This is a very most natural way of providing the operand address as part of the instruction, and it is very simple, does not involve any computation. That means the address which is used to get the operand from the memory, this is your main memory. Effective address is used, this is a term which is used for pointing to the operand. So here effective address is the address which is provided as part of the instruction. So this addressing mode is although simple, but depending on the size of the address, the full address has to be provided as part of the instruction. For example, in case of your 8085 microprocessor, the address is 16-bit. So if you are fetching some operand, it will require, first of all, you have to fetch the address, which will involve 2 memory cycles, one read cycle to get this address, lower order byte of address, another fetch cycle, read cycle to get this higher order byte of address. Then that address will be used to fetch this particular operand from the memory. So you will require 3 machine cycles or 9 clock cycles to get the operand before you can perform the computation. So later on we shall discuss about this type of the instructions involving the direct or absolute addressing. Then comes the indirect mode of addressing. In indirect mode of addressing, instead of directly providing the address as part of the instruction, here is your opcode, then your address is here. Now this is not the address of the operand. So this is pointing to a memory location. This is your main memory. This will point to, obviously this is byte organized, and you will require 2 locations. So it will point to the first byte, and these 2 bytes will be the address of the operand. That means this will be used to point to another memory location where your operand is stored. This is your operand. So this address is not providing the address of the operand, but it is pointing to another address which is pointing to the operand. So in this particular case, the effective address is essentially the content of the memory location of the address provided as part of the instruction. So this particular addressing mode is slow. Why slow? Because you have to first you have to use 2 read cycles to read this address, then another 2 cycles to read this address, then finally you can get this operand. Then you may be asking, if it is so slow, why it is being used? The reason for that is it is very flexible. It is a very flexible way of providing the address. For example, without modifying the program, this is your program, part of the program. Without modifying the program, just by changing this value, you can point to another memory location. So this kind of flexibility is provided by indirect mode of addressing. That's why it is widely used in almost all microprocessors, in many microprocessors. Then comes the register addressing. As I told you, one of the main objective of addressing modes is to specify address with smaller number of bits. And obviously, if we assume that the registers are the first few memory locations provided as part of the CPU, then registers can be used to store operands instead of storing them in memory location. Some of the operands can be stored in the registers itself. So in such a case, you will see you don't require a large number of bits. That with a very small number of bits you can access the operands stored in the registers. For example, here is your program opcode. Then as part of the opcode, you are providing the address of the register. That register will be, and this is your register bank. You can have a number of registers, and it will point to one of the registers, so this one, and here is your operand. You are not getting your operand from the main memory, but you are getting from the operand, from the register bank. And obviously, as you can see here, the instruction is sort. If you remember, I used this kind of instruction. For example, this one 0 1 0 0 0 1 1 1. This is the instruction move A to B. You are transferring data from one register A to another register B. And you can see here you require only 1 byte, and the execution time is only 1 machine cycle or 4 clock cycles. So you can see only a small part, and in fact in this part is the address specifying this accumulator, the source, and this part is specifying the destination, register B. So register B is specified by these bits 0 0 0, and register A is specified by these 3 bits, and only this part is opcode. So just by 1 byte you are able to refer to an operand. So it is sort. It allows you to write sort program, and it is faster in execution. However, one limitation is that when you cannot, you have to transfer that operand beforehand to the register, as we have done in this particular case. For example, this operand was initially transferred to the accumulator. Only then you are able to perform register operation. This will be necessary, but during runtime, this kind of intermediate results will be generated and will be processed inside the processor. So those intermediate results which will be used can be stored in these registers. And obviously, it also involves a little complexity, because the programmer has to keep track of all the registers that is being used to store the intermediate results. For example, if an interrupt comes, then the programmer has to store all these registers in the stack, and whenever it comes out of the subroutine or interrupt, it has to restore those registers. So it needs little bit of housekeeping. So programming becomes little complex, but it gives you dividend in terms of shorter size of program and faster execution. That's why these are widely used. One extension of this register mode of addressing is register indirect. In register indirect mode of addressing, what you do, you give the address of the register as part of the opcode itself, and that points to, you may have more than one such registers. For example, register pair. For 8-bit microprocessors, you cannot really hold an address in one register, so you have to use a register pair. So you can use BC, DE or HL in case of 8085, and that register pair provides you the address. 16-bit address is stored here, and it will point to a memory location. This is your main memory, and here is your operand. So this is how you can referent by using register mode of register indirect addressing, and this is widely used again because of flexibility. Obviously, this register indirect mode of addressing is faster than this simple indirect addressing mode, because you don't have to read the register pair. It is provided as part of the instruction, and this register pair is also part of the CPU. That's why this earlier you were reading this address, then this address, then getting the operand. But here you will not require any additional memory cycles to read the register pair or the address from the register pair, because these are part of the CPU or the microprocessor. Then you will straight away you can get the address of the operand. So you are getting the flexibility at a very low overhead, which is associated with that high overhead is associated with indirect addressing. That's why register indirect is preferred over indirect mode of addressing by the programmers. Then comes another addressing mode, that is paged addressing. As I was telling, because of the locality of reference, usually you are executing a program within small part of the memory. And since you are executing within a small part of the memory, because of the locality of reference, you can use a small number of bits to refer to that address. For example, you can use the concept of paging. What can be done? Say, suppose this is your main memory, starting from 0000 to FFFF in hex. Now you can divide the entire address space, that memory, into pages each of say 256. So to refer to any location within that page, you require 8-bit. Suppose then what you are essentially doing, if you are having 16-bit address, say A0 to A15, this is your 16-bit address, you are dividing into two parts, A0 to A7 and A8 to A15. Then this A8 to A15 is referring to the beginning of a page, and this part, the lower order 8-bit, is referring to any location within this page. So what you can do, this particular part, the higher order byte, can be stored in a register. We may call it direct page register. Then in your instruction you can provide only this part. So instead of 16-bit, you will use only 8-bit as part. You will store 8-bit as part of the instruction. But obviously your program must be in this range. Then only then you can refer to any location in the memory by using this paged addressing. So this is what is done in case of your paged addressing. Your program, this is your opcode, and this is your address. But here the address is 8-bit. What you are doing, you are using that direct page register to hold the higher order byte of address, and the 8-bit, the lower order byte is provided as part of the instruction. Then you are concatenating these two higher order byte is here, lower order byte is here. You are concatenating them to generate a 16-bit address to refer to any operand in the memory. Here is your operand. This is how you are generating. Obviously, it is very fast. It is fast because you require only 1 byte to be read from the main memory to get the address, and direct page register is always part of the CPU. So you immediately get this, then in the next cycle you can generate this address to get the operand. In some particular processors, the this direct page register is not provided. So even then it is possible to provide page addressing in a very limited way, and that is called zero page addressing. How zero page addressing is done? Suppose this is not there, direct page register is not provided. What you can do, that you allow this page addressing only for the 0th page. That means as long as your program is within these locations, that means 0000 to 00FF, then you assume the higher order byte to be 00 in hex, and lower order byte is provided as part of the instruction. So that's how you can generate this zero page addressing without the direct page register. In some microprocessor, this zero page addressing is also provided because it is faster and require smaller space in the program. Then comes the indexed addressing. In indexed addressing, you use a special register known as index register. Here is your opcode, and here is your index register, and that index register holds some data, some address part, and the instruction is also provided with some base address. Then what you do, this instruction register which holds some offset value is added with this base address provided as part of the instruction to generate the effective address. So your effective address in this case is equal to effective address is equal to content of the index register plus this base address which is provided as part of the instruction, and this is used to refer to a memory location where your operand is being stored. And this particular addressing mode is used to implement array. How? Suppose you have stored some program, a table or an array has been stored here. This is an array. What is being done? The starting address of the array is provided by that base address. Base address points to the beginning of the array. Then this index register which is provided here points to an element within that array. For example, if it is here, this offset is provided as part in the index register. So you can implement an array with the help of this indexed addressing, and you can access different elements of the array just by changing this content of the index register. Index register can be changed to point to any element of array. If it is 0, it will point to the first element. If it is 1, it will point to the next element, and so on, without modifying the base address. And to facilitate accessing arrays one after the other, sometimes auto increment, auto decrement, or increment is provided depending on in which order the array is stored. You can you can access different elements, and the index register is automatically decremented or incremented to point to different elements of that array. And somewhat similar to this addressing mode is there is another addressing mode that is known as based addressing. In based addressing, again you are using a special register known as base register to hold some value, and here is your opcode, and here is some displacement, and the address generation is done more or less in the same way. Only difference is that instead of using index register, you are using the base register. So the base content of the base register is added with the displacement to generate the address of the operand. Here is your operand. Now in this particular case, as you can see here, the base register is providing some offset. Here is also some offset, and which is added with the displacement to get the operand. You may be asking, in what way it is different from indexed addressing, and why a separate addressing mode has been provided although the address generation mechanism is identical. Actually, the purpose of based addressing is different. Based addressing is commonly used for the purpose of relocation. Later on, whenever you will study virtual memory, you will see that at different instances of execution of a program has to be relocated at different parts of the memory, and that can be done by using this based addressing. How it is done? So it is used for relocation. How it is being done? In this particular case, that base register holds the base address. Say this is pointing to this. Then with respect to that base address, the offset is provided as, or the displacement is provided as part of the instruction. So you are adding the content of the base register to the displacement to point to any other location, and you can transfer it here. Now suppose initially your program was here. That time the base register value was something. Now you want to change this program, entire program has to be shifted to another part of the memory. What you can do, the base register can be modified to point to this memory location, and now this is where is your program is shifted by changing the content of the base register. Now within this program, that displacement, using the displacement, again you can refer to any location to get an operand. So this is how the relocation can be done by changing the base register. You may be asking, in what way it is different from the index register, indexed addressing? The main difference comes from this fact. in case of indexed addressing, you are changing the index register to get different elements of the array. How you are doing? We have seen that index register is being modified. Index register is being modified to refer to different elements of the array. That means in indexed addressing, that index register is variable. The value in the index register is changing. It is incremented or decremented to point to different elements of the array. You are keeping the base address fixed, and that's why the base address must be a full address. On the other hand, if your array is of smaller size, the offset can be of say 8-bit. Suppose your array has got only 256 elements. So in that case, this index register can be of 8-bit, need not be of full 16-bit. So this base address is provided here, and by using an index register of maybe smaller size, you can refer to different elements of the array. But in case of base addressing, the situation is different. The base addressing is providing is the full address. Either it is referring to this memory location or referring to this location. And once it is initialized during the running of a program, when you are executing the program, at runtime, you are not modifying this value of the base register to refer to an element, I mean any operand address. What you are doing, you are changing this displacement. So in this case, the displacement is variable. In the previous case, the index register was changing, was variable. This was fixed. That base address was fixed. In case of base addressing, the base register is fixed. This is fixed, and this is variable. And that's how. This is the way these two are different. And in base addressing, this need not be full address, but the base register must be full address, 16-bit. This has to be 16-bit. This can be of smaller size. Now, by combining index mode of addressing and base mode of addressing, some combination known as best indexed addressing is also provided, which is essentially a combination of indexing as well as best addressing. You can use an index register and base register to have a combined effect. Then comes the relative addressing. In relative addressing, what you are doing as part of the opcode, you are providing some displacement. This is your displacement, and this displacement is added with the program counter. Added with the program counter to generate the effective address. So effective address is generated by adding the displacement with the program counter to refer to an operand address. And this particular addressing mode is very popular in branch instructions. In branch instructions, what you do, suppose your program this is the memory, this is the range over which your program is being stored. Now, within this program, you may be looping between this part. And so, the program counter was pointing at this point, let's assume. Then with respect to program counter, this offset value, the displacement can be provided will be added to the program counter to jump to this location. So this kind of looping can be done or jumping can be done within a program. And this has one advantage, that since it is with respect to the program counter, depending on the value of the program counter, the entire program can be shifted. Suppose this program is now shifted to this, shifted here, and you are again looping from this to this. Now since it is with respect to the program counter, if your program is shifted from here to here, even then it will execute correctly, and that's how the position independency can be implemented. You can write position independent program by using this PC relative instructions. So this relative mode of addressing facilitates position independency. Independent, dependent. Okay. Finally, we shall discuss the last addressing mode, that is your stack addressing. In stack addressing, what you do, your opcode is simple, and you already know that there is a stack pointer SP, with the help of which stack is implemented, and stack pointer is initialized with some value, and stack pointer points to the bottom of the stack. Then if you initially suppose, so this is your main memory where stack is implemented, and stack pointer is part of the CPU. Initially, let's assume this location immediately above the bottom is empty. These are all empty. Now suppose you execute one instruction known as push. Whenever you execute the push instruction, then in this empty location, say push A, some value, operand value is being stored. So operand A will be now will be in that empty location, and that stack pointer will point to this location. If you perform another push, what you are doing, you are decrementing the stack pointer by 1 and pointing to the next location where the operand is stored. Now if you push another data, then automatically your A is here, say push B is here. Now the stack pointer points to this location. You can perform reverse operation known as pop. Say if you perform pop. If you perform pop, then you will be taking out the first element, this element first, then this element. That's how you are implementing a data structure known as LIFO, last in, first out. So data structure known as LIFO can be implemented by stack. And this stack mode of addressing is not only suitable for implementing the data structures like stack, it also helps you in implementing subroutine call. In implementing subroutine call, whenever there will be a subroutine call, as you know, whenever subroutine call occurs, later on we shall discuss in more details, you will see that the existing value of program counter and some other registers which are used in the existing program has to be stored in stack in some location, and whenever you will be returning, you have to read them from stack. So this stack addressing, with the help of this stack addressing, that can be very easily done. And this stack addressing also facilitates re-entrancy. A program can be made re-entrant with the help of this stack addressing, because whenever you are calling it once again, the previous values up to a certain point that has been executed, that information can be stored in the stack. So re-entrancy can be implemented by this stack addressing. So we have given an overview of different types of addressing modes which are available in microprocessors. Now let us very quickly refer to the addressing modes supported by 8085. 8085 supports a very limited number of addressing modes. One is inherent. Inherent addressing mode is supported by 8085. It supports immediate addressing modes. It supports direct addressing mode. It supports register addressing mode. It supports register indirect addressing mode. It also supports stack addressing mode. But unfortunately, the 8085 does not support index mode of addressing, base mode of addressing. So, but to start with, these addressing modes are sufficient to write program, and later on in the next lecture we shall discuss how various addressing modes, data types and instruction formats are combined to realize the instruction set of 8085. Thank you.